Hello friends, in the last session we have seen what is Gauss law and we have also seen the divergence theorem. Now today in this session we are going to see work done in moving a point charge and we are also going to see electric potential. So let's start this session. So consider a point charge q is there and we wish to move this point charge q at a distance dl in an electric field. Present electric field is considered E. So a point charge is there and we want to move that point charge from one place to the other place. So let that distance is dl. So the force on q due to the electric field is given by the equation force is equal to capital Q into electric field intensity, where this suffix E represents here this is the force due to electric field. So the force due to electric field, it is Q into E, because we know that electric field intensity, it is equal to force per unit charge. Therefore from that equation we can write force is equal to charge into electric field intensity. Now the component of this force in the moving direction, that is dl direction, which we must overcome, it is written as F suffix E into L. So it can be given as force dot with unit vector in that direction dl. So it is written as al. So F dot al, and we know that value of F is q into E dot with al bar. Now to overcome or to get this dot product possible, so the force which we must apply, it should be equal and opposite to the force due to the field. So the applied force is minus Q electric field intensity dot with AL bar. Now here minus sign is kept because this is the force exerted by external agent. Therefore our expenditure of energy is the product of force and the distance. So therefore force is given as minus q into E dot with AL bar. Now this force is applied for moving a point charge for a very small distance dl. Therefore what the work done is going to be happen here, it is the differential work done. So the differential work done by external source for moving point charge q, it is given by minus q into electric field intensity dot with al dl bar. Now in general this can be written as minus q into E dot with dl bar. Clear? So this is the differential work done, therefore it is denoted by dw, where w is the notation for work done. So part of that work done or small work done can be represented as a dw. So it is minus q into electric field intensity dot with dl bar, where dl is the very small distance. So this is the small work done equation while moving a point charge q. Now consider we want to calculate the total work done in moving this point charge. So the total work done is denoted by W. Here total work done can be written as W is equal to integration of dW. Therefore we can write total work done W is equal to minus Q integration of E bar dot dl bar, and this integration limits, it is from initial point to final point. So in this equation Q represents the charge present, E is the electric field intensity, and this dl, so it can be written as small dl also, it is the differential length. Therefore we can calculate the total work done in moving a point charge q from initial point to final point. Now here if suppose problems is based on this work done calculation, suppose, then q will be given to you, electric field intensity will be mentioned to you. You just have to write the equation of dl by observing in which coordinate system this particular situation is given. So the differential length equation in different coordinate system we already seen, but we will revise here. So dl for Cartesian coordinate system can be written as dx ax bar plus dy ay bar plus dz az bar. For the cylindrical coordinate system, differential length is given as dl bar equal to dr ar bar plus r d phi a phi bar plus dz az bar. For the spherical coordinate system, dl bar can be written as dr ar bar plus r d phi a phi bar plus r sin theta d phi a phi bar. So in this way, this work done equation can be used to solve the different problems or for the calculations of work done in moving a point charge. Now we'll see the simple problems. So let electric field intensity E bar is given as minus 8xy ax bar minus 4x square ay bar plus az bar volt per meter. Now it is asked to find the work done in carrying a charge of 6 coulomb from point A having coordinate 1, 8, 5 to point B having coordinate 2, 18 and 6 along the path y is equal to 3x plus 2 and z is equal to x plus 4. So the electric field intensity is given here, charge value is given here, initial point and final point is given here, and the path through which the charge is moving, it is also mentioned here. So the work done can be written as W is equal to minus Q integration from initial point to final point E bar dot dl bar. Now the expression for dl bar can be written as, here if you observe this E and if you observe these coordinates, this dl bar can be written in a Cartesian coordinate system here. So dl bar equal to dx ax bar plus dy ay bar plus dz az bar. Therefore work done, it can be given from this equation as minus q integration initial to final E bar dot dl bar. So put the q value here. Now q given here, it is 6 coulomb. So W is equal to minus 6 integration initial point to final point E bar, it is minus 8 xy ax bar minus 4x square ay bar plus az bar dot with dl bar, that is dx ax bar plus dy ay bar plus dz az bar. Now you take this dot product first. So while taking this dot product, you simply see the possible dot products here. So here minus 8xy ax bar dot with dx ax bar, it is possible. Therefore we can write this answer as minus 8xy dx. Similarly minus 4x square ay bar dot with dy ay bar, it is possible. Therefore we can write here minus 4x square dy. Similarly az dot dz dot az bar, it is possible. So we can write this answer as dz here. Clear? So work done is minus 6 integration from initial point to final point minus 8xy dx bar minus 4x square dy bar plus dz bar. Now simplify this integration to get the final answer. But here if you observe the given path, so path given here, it is y is equal to 3x plus 2 and z is equal to x plus 4. So this path is mentioned here. Therefore we'll make use of that path here. So if I write y is equal to 3x plus 2, then it will give me, if I differentiate on both sides, so it will give me dy, it is equal to 3 dx. Similarly z is equal to x plus 4. If I differentiate on both sides, so it will give me dz equal to dx. Now we'll try to write all the variables in terms of x only. So here all the variables are mentioned as x, y, z. Clear? So we'll write all the variables, that is x, y and z, in terms of x only. So for that we'll take the help of this path. So we'll rewrite the equation as w is equal to minus 6 integration. Now put only x coordinate. So x varies here as like 1 to 2. So we'll put the limit as 1 to 2. So integration from 1 to 2 minus 8x y dx is there. Clear? So instead of y, we'll put here 3x plus 2. So minus 8x in bracket 3x plus 2 dx. Now the second term here it is minus 4x square dy. So minus 4x square, instead of dy we'll put dy as 3dx plus integration of plus dz term is there. So instead of dz we'll put dx. So plus dx term. Now evaluate this integration because all terms are now in the only one variable, that is x. So if you evaluate this integration, we'll get, if I take this minus side outside of this, so we'll get here minus 6, that is plus 6, integration 1 to 2. So it will become 8 3s are 24 x square plus 4 3s are 12 x square. So 24 plus 12 it is 36 x square. Then 8 2s are 16x, so plus 16x, and the remaining term is minus 1. Clear? So if I write this equation, if I take the dx common here, so it will become 36x square plus 16x minus 1 dx. Now evaluate this integration to get the final answer. So this will become 6 in bracket 36 integration of x square, and integration of x square is x cube by 3, put the limits 1 to 2, plus 16 integration of x becomes x square upon 2, put the limits 1 to 2, minus integration of dx. So integration of dx is x, put the limit 1 to 2. Now after putting the limits, evaluate this integration, so you will get the final answer as 642 joule. So this is the final work done answer, that is 642 joule. Now we'll see next problem. So it is asked to find the work done in bringing a point charge of 5 microcoulomb from origin to the point P having coordinate 2, -1, 4 through the electric field intensity 2xyz ax bar plus x square z ay bar plus x square y az bar volt per meter through the path. So first path mentioned as straight line segment, that is from origin to 200 to 2 minus 1 0 to 2 minus 1 4. So in the first path it is mentioned that you are moving the charge from origin to the final point, that is 2 minus 1 4. Now it is also asked to calculate the work done through the path having a straight line, x equal to minus 2y and z equal to 2x. So these two paths are mentioned here. So we'll evaluate this problem here. So we'll consider the first path, that is straight line segments. So you can observe here in this diagram. So this is the x axis, this is the y axis, this is the z axis. Now the initial point is origin 0, 0, 0. Then point is moved to x value 2, y value 0, z value 0. So the point, so this point charge is going to be moved at 2, 0, 0 on x axis itself. Now the next point where the charge is moved, it is 2 minus 1 0. So you can observe here this point is 2 minus 1 0, means y value here it is possible as -1. So we are going to move this point towards left by -1. Now this 2 minus 1 4, 2 minus 1 0 point is raised by a height of 4. Therefore, we will raise this point along z axis by a height of 4. Therefore, we are going to get this point as 2 minus 1 4. Clear? So this is our origin and this is our last point, that is 2 minus 1 4. So our charge can be moved from this origin to this point directly like this, but here the path is mentioned as it is going to move like this to this to this, and this to this. Clear? So this is our first path mentioned here. Now we'll consider these separate straight line segments and we'll evaluate this work done. So for the segment 1, dl bar can be written as dx ax bar because it is along x axis. Therefore the dl bar can be written as dx ax bar, and y and z is going to remain 0. Now for the segment 2, you can observe this is the segment 2. So for segment 2, dl bar can be written as dy ay bar because this is along y axis. Now for this case, x is going to remain constant as 2 and z is going to remain 0. Now for the segment 3, you can observe this segment 3. So here it is along z axis, therefore dl bar can be written as dz az bar. So for this, x is always 2, y is always minus 1. So what is changing here? Only z value is changing. Clear? So the total work done along these different segments can be written as, so we'll evaluate the work done for different segments. So we'll write for first segment, that is W1, that is first work done. So W1 it is equal to minus Q integration initial point to final point E bar dot DL bar. So it can be written as minus, so Q is given as 5 microcoulomb. So 5 into 10 raised to minus 6 integration x varies from 0 to 2. Now given E bar is 2xyz ax bar plus x square z ay bar plus x square y az bar dot with dl bar. Now for segment 1, dl bar is dx ax bar. So we'll write here dx ax bar. So therefore 2xyz ax bar dot with dx ax bar, this dot product is the only possible dot product here. So if I evaluate this, so I will get it is equal to minus 5 into 10 raised to minus 6 integration from 0 to 2 2xyz dx. Clear? Now if you observe this equation for the segment 1, it is coming as 2xyz dx. Now here y and z are 0. Therefore if I evaluate this integration, I am going to get final answer as 0 because y value and z value here it is 0. So we will get W1 or work done in moving a point charge from or along segment 1, it is 0. Now we will consider the second segment. So second segment is what? From 2 0 0 to 2 minus 1 0. So this is our path. So for this path we can write second work done, that is W2. So it is equal to minus 5 into 10 raised to minus 6 integration. Now here y is varying from 0 to minus 1. Therefore the limits it is 0 to minus 1 x square z dy. Now you can see the second part here, it is mentioned as y component, it is x square z ay dot with dy ay bar. So this dot product will result as x square z dy. Clear? Now it is also multiplied by z. Therefore we already know that z value is 0 here for this segment. So if we evaluate this integration, we are going to get this answer as 0. So the work done for the second segment it is 0. Now for the segment 3, we'll calculate the work done. So we'll denote this work done as W3. So W3 it is equal to So you can see here, this is the segment 3. So for the segment 3, x is always 2 and y is always -1. Only z term is changing. And dl bar for segment 3 can be written as dz az bar. So w3 it is equal to minus 5 into 10 raised to minus 6 integration from 0 to 4. Now see this equation, e bar it is 2xyz ax bar plus x square z ay bar plus x square y az bar. So from this only z component we are going to consider. So that z component is x square y az bar dot with dz az bar. So it will result as x square y dz, and the limits for this integration it is 0 to 4. So if you evaluate this integration, here y is going to remain -1 and x is going to remain as 2. So x square y it can be taken outside of this integration. So minus 5 into 10 raised to 6 x square means 2 square into y means -1, and integration of dz it is z. Put the limits for this evaluated integration as 0 to 4. If you simplify this, you will get this answer as 80 joule. So 80 microjoule. Therefore, the work done for segment 3 is 80 microjoule. So the total work done it is W1 plus W2 plus W3. So it is 0 plus 0 plus 80 microjoule. So you will get final answer as 80 microjoule. So this is our total work done in moving a point charge from this initial point to final point. Clear? Now for the second path, the second path is mentioned as, it is asked to calculate the work done along the straight line mentioned as x equal to minus 2y and z equal to 2x. So it is the direct path to go from 0 0 0 to our given point, that is 2 minus 1 4. So all coordinates are changing. So the dl bar, as it is a Cartesian coordinate system, we can write dx ax bar plus dy ay bar plus dz az bar, and we know the basic work done equation. So work done can be written as minus q integration e bar dot dl bar. So it can be written as minus q means 5 microcoulomb, so minus 5 into 10 raised to minus 6 integration initial point to final point. Now e bar dot dl bar, so it is evaluated. So we got this answer as 2xyz dx plus x square z dy plus x square y dz. Now here path is mentioned, so we have to follow that path. So that path mentioned is x is equal to minus 2y and z equal to 2x. So for x equal to minus 2y, we can write y is equal to minus x upon 2. This will result, if I take the differentiation on both sides, so this will result dy equal to minus dx upon 2. Similarly, z is equal to 2x. So from this we can write, by taking the differentiation on both sides, we can write dz equal to 2 dx. Now writing the expression using these above differential equations and putting all these equations in terms of x and using the limits for x only, so we'll write w is equal to minus 5 into 10 raised to minus 6 integration. Now x limit, x varies from 0 to 2, 2x. Now here it is 2x multiplied by y into z. Clear? So we'll put all the replacements for y and z here. So y becomes here x upon minus x upon 2 and z becomes here 2x. So we'll keep this 2x minus x by 2 into 2x dx plus, you observe the second term, it is x square z. Now put z here as 2x. So x square into 2x and dy term is there. So dy can be written as minus dx by 2 plus x square y dz. So this can be written as x square. Instead of y we can write minus x upon 2 into dz. So dz can be written as 2 dx. Now all these integration equation can be written using one variable, that is x. Now it is very easy to evaluate this integration. So simplify these equations and try to evaluate this integration. So we'll get minus 5 into 10 raised to minus 6 integration from 0 to 2. So if I evaluate this, or if I simplify this first, so we'll get here minus 2x cube dx. Now for the second term we'll get here minus x cube dx, and for the third part we'll get here minus x cube dx. So all it is written in terms of dx here. Now if you evaluate this, so this is minus 2 minus 1 minus 1, so it will become minus 4 x cube dx. So evaluate this, minus 5 into 10 raised to minus 6 integration 0 to 2 minus 4 x cube dx. So if you evaluate this integration, you will get minus 5 into 10 raised to minus 6 into minus 4 in bracket integration of x cube, that is x4 divided x raised to 4 divided by 4, limits 0 to 2. So if you evaluate this, you will get final answer as 80 microjoule. Now you can observe here the work done given for the what evaluated for the first segment or first part, that is using different segments, we got the answer as 80 microjoule, and the work done calculation for this given straight line path, we got this answer as also 80 microjoule. So it says that work done is independent of the path. Your initial point and final point is given, so you can go by using any path towards your destination. So work done is independent of path. Now we will see one next important point, that is electric potential. So just we have seen the equation for the work done in moving a point charge from initial point to final point. So the total work done in the presence of electric field intensity while moving a point charge from initial point to final point, so that can be given as W is equal to minus Q integration initial point to final point E bar dot dl bar. Clear? Now we want to calculate the potential. So work done per unit charge, it is called as potential. So in the same way as we define the electric field intensity as the force on a unit test charge, now we are going to define the potential difference V as the work done in moving a unit positive charge from one point to another point in the presence of electric field. So as we mentioned the definition of electric field intensity considering that force per unit charge, on the same line we are going to calculate now work done per unit charge. So this concept or this definition, work done per unit charge, is called as potential. So we are having the equation of W here. So if I write or if I take this Q at this side, means LHS side, so it will become W upon Q. So what remains on the RHS? At the RHS side we are going to get here minus integration E bar dot dl bar. This is nothing but the potential, because potential is work done per unit charge. So the potential equation can be written as V is equal to minus integration initial point to final point E bar dot dl bar. Actually this is the potential difference equation. Why? Because we are writing here initial point and final point. Potential is different and potential difference is different. So these are the two separate terms are there, potential and potential difference. So V is equal to it is minus integration of E bar dot dl bar. Now we will try to write the equation of potential difference considering the electric field intensity and the differential length. So we can try out this definition by finding the potential difference between point A and point B at radial distances. So let those distances are r suffix A and r suffix B from a point charge Q. So considering the origin, it is at the where my charge is present. So I can write electric field intensity. Now assuming the cylindrical coordinate system, I can write this electric field intensity as ER dot AR bar. Means this is the electric field intensity due to point charge. So I can write this equation as E due to point charge as Q upon 4 pi epsilon naught R square AR. Similarly, the differential length can be written as dr AR bar. Now I want to write the potential from A to B. So this can be written as minus integration initial point to final point. Please remember that here initial point is B and final point is A. So minus integration B to A E bar dot dl bar. So the initial point can be written as distance from origin to that initial point. So that is RB, and final point can be written here as distance from origin to that final point. So it is R suffix A. It is integration E bar. So E bar can be written as Q upon 4 pi epsilon naught R square into dl bar. So it is dr. AR bar dot AR bar, it will result 1. So this is minus integration initial to final Q upon 4 pi epsilon naught R square dr. So it will become Q upon 4 pi epsilon naught. If I evaluate this integration, so I will get 1 upon R, and putting the limits RB to RA. So it will become 1 upon RA minus 1 upon RB. So if I separately evaluate this, so it is Q upon 4 pi epsilon naught RA minus Q upon 4 pi epsilon naught RB. So this is the potential from B to A. So it can be written as V suffix AB. So it is VA minus VB, where VA is the potential at point A and VB is the potential at point B. So potential at point A can be given as Q upon 4 pi epsilon naught RA, and potential at point B can be given as 1 upon 4 pi epsilon naught RB. So the potential at any point is the potential difference between that point and a chosen point at which the potential is 0. So V suffix AB can be written as VA minus VB, where A is the final point, B is the initial point. In, in some of the books, this equation is written as VAB as VB minus VA, where A is the initial point and B is the final point. But here we considered as A as the final point, B as the initial point. Now we'll see this equation and we'll write some of the observation from this equation. So VAB, it is equal to VA minus VB. So from this we can write, if VAB, in this case A is the initial point. Now see here, I have considered A as the initial point while B is the final point. Clear? So this can be, from this, if this is the situation, then we can write, if VAB is the negative, then there is a loss in potential energy while moving a point charge Q from A to B. So this implies that work is being done by the field. If potential is negative, then it implies that work is being done by the electric field. If VAB is positive, then there is a gain in potential energy in the movement. So an external agent is going to perform the work here. Now we have already seen the problem that you go by any way from initial point to final point by using any path, you are going to get the same answer there, same work done. So we can say that potential is independent of the path taken. You can take any path, your source point and destination point, if it is same, then you are going to get same answer. The VAB is the potential and it is measured as joules per coulomb. Here we considered A as the final point, B as the initial point. Now while writing all these comments, as far as especially this first, we considered A as the initial point, B as the final point. Clear? So do not get confused in between this. Now we'll write one simple equation, that is potential due to point charge. Please remember this equation. Potential due to point charge is given by the simple equation. That equation is V is equal to Q upon 4 pi epsilon R, where R is the distance of a point for which we are going to calculate the potential. Now as far as free space is considered, we can write potential is equal to Q upon 4 pi epsilon naught R. Now we'll get one important relation between electric field intensity and potential. Consider the situation as shown in this figure. So this is these lines indicates the presence of electric field E, and let we are moving the point charge from this initial point A to this point B. So let we are moving the charge from A to B. So A is our initial point here and B is the final point. VBA as minus of VAB, because if you travel from A to B, then you are going to get one potential, and if you are going to travel from B to A, then that potential is same but direction is opposite. Therefore minus sign is mentioned here. So if you do the addition of all these two potentials, that is VBA plus VAB, then we are going to get this answer as 0. So this implies that from the definition of potential, so definition of potential, it says that V is equal to minus integration of E bar dot dl bar. Clear? But if I write that for A to B and B to A, means we are traveling like this. For example, suppose this is A to B and we are traveling from B to A. Let this is the, if you observe this total path, so it is the closed path now. Clear? So for the closed path, integration E bar dot dl bar, it is going to result 0. Why? VBA plus VAB, these are the same values but opposite in direction, therefore plus minus, so it will become 0. So in general I can write integration E bar dot dl bar, it is equal to 0, but this integration is for closed path, therefore closed loop integration of E bar dot dl bar, it is equal to 0. So this shows that the line integral of E along a closed path as shown in the figure, it must be 0. So physically it implies that there is a no work done in moving a point charge along this closed path. Still electrostatic field is present there. So we are going to get work done as 0 there. Clear? Del cross E, it must be equal to 0. So this itself is one of your Maxwell's equation, that is we can say the conservative property of potential here, conservative nature of electric field intensity. So del cross E, it is equal to 0. Now we'll consider the potential as V equal to minus integration E bar dot dl bar as per our already derived equation. Now here if I want to write the elemental potential, means potential due to small length, potential due to small differential length, then dV it is equal to E bar dot dl bar. Now considering E as Ex Ax bar plus Ey Ay bar plus Ez Az bar, and dl as Dx Ax bar plus Dy Ay bar plus Dz Az bar. So we'll get this answer as minus Ex Dx minus Ey dy minus Ez dz. So this is the value of small differential potential, that is dV. Clear? But we know that dV can be written as derivative of V with respect to x plus derivative of V with respect to y plus derivative of V with respect to z. So by observing these two equations, this dV and this dV, from these two equations we can write, after comparison we can write Ex equal to minus dV by dx, Ey equal to minus dV by dy, and Ez equal to minus dV by dz. So this is nothing but, if you observe this equation, this is nothing but gradient of V. So we can write directly here, electric field intensity, it is nothing but gradient of negative potential. So E, it is equal to minus of del V, that is E is equal to minus of gradient of potential. So the electric field intensity is mentioned as negative of gradient of V. So the negative sign shows here that the direction of electric field is opposite to the direction in which potential increases, and E is directed from higher to lower levels of potential. So this is the most important relation, E is equal to minus del V. Now we know that gradient in different coordinate system can be mentioned as, so dV, it is equal to dV by dx Ax bar plus dV by dy Ay bar plus dV by dz Az bar, as far as Cartesian coordinate system is considered. For the cylindrical coordinate system, dV can be written as dV by dr Ar bar plus 1 by r dV by d phi A bar plus dV by dz Az bar. For the spherical coordinate system, del V can be written as dV by dr Ar bar plus 1 by r dV by d phi A bar plus 1 upon r sin theta dV by d phi A bar. So these are the different gradient equations considering different coordinate system. Now we'll see simple problems based upon this potential equation. So let 2 point charges are given as minus 4 microcoulomb and 5 microcoulomb. Those are located at point 2 minus 1 3 and 0 4 minus 2 respectively. Now it is asked to find the potential at point 1 0 1, assuming zero potential at the infinity. So the situation is like this. The situation is like this. Uh, this is the first point charge which is placed at 2 minus 1 3. That first charge is minus 4 microcoulomb. This is the second point charge which is located at 0 4 minus 2, and the value of that second charge is 5 microcoulomb. And let this is the point of interest, point P, where we are going to calculate the potential because of these 2 point charges. So this point is 1 0 1. So first we'll calculate the distance between first charge and this point of interest, and the distance between this second charge and this point of interest P. So let this distance is r1 and this distance is r2. So the distance between 2 points is calculated. So the distance between these 2 points is calculated here. So r1, it is equal to square root of 2 minus 1 bracket square plus minus 1 minus 0 bracket square plus 3 minus 1 bracket square. So it is root 6, and the distance r2, it is square root of 0 minus 1 bracket square plus 4 minus 0 bracket square plus minus 2 minus 1 bracket square. So this results as root 26. Now potential due to point charge, that equation we are going to use here. So potential at point P due to charge Q1, it is V1, it is equal to Q1 upon 4 pi epsilon naught R1. Now put the value of Q1 epsilon naught and distance R1 and simplify this. We will get this answer as minus 14.7 kilovolt. Similarly, calculate the potential at point P due to charge Q2. So it is V2, it is equal to Q2 upon 4 pi epsilon naught R2. Now put the value of Q2 epsilon naught and distance R2 and simplify this. We will get this answer as 8.83 kilovolt. Now potential due to Q1 and potential due to Q2 at point P is calculated. Now the total potential at this point P, it can be given as V1 plus V2. So it is minus 14.7 plus 8.83 kilovolt. So we'll get this answer as minus 5.87 kilovolt. So this is the net potential at point P. Now we'll see the next problem. It is find the potential of point P having coordinate 1, pi by 2, 3 with respect to point Q having coordinate 3, pi by 4, 2 if the electric field is given as E bar equal to 100 upon R AR bar. Now if you observe the coordinates given here, it is 1 pi by 2 3 and it is 3 pi by 4 2 means R phi z means it is cylindrical coordinate system. So we are going to use the equations mentioned as far as cylindrical coordinate systems are concerned. So for the cylindrical coordinate system, differential length dl bar, it is equal to dr ar bar plus r d phi a phi bar plus dz az bar. Now the potential of point P with respect to point Q. So it is V suffix PQ. So it can be written as minus integration E bar dot dl bar. Integration limits are from Q to P. So it is minus integration from Q to P. E bar, it is 100 by R AR bar, 100 upon R AR bar dot with dl bar, and dl bar is dr AR bar plus r d phi a phi bar plus dz az bar. Now simply take the dot product here. So AR bar dot AR bar, it is possible here, and all other dot products are not possible here. So if you simplify this dot product, we are going to get this answer as 100 upon R dr, and the limits are considered here 3 to 1. So if we evaluate this integration, we will get as minus 100 natural log of R limits from 3 to 1, and if we evaluate this, we will get this answer as 109.86 volt. So this is the potential of P with respect to Q.